Imagine stepping onto a high-speed train in Madrid and arriving in Casablanca just hours later. No flights, no ferries, just solid ground beneath your feet as you travel between two continents. This isn't fantasy. Spain and Morocco are bringing back one of the world's most ambitious tunnel projects. A $10 billion underwater passage that could change everything we know about travel between Europe and Africa. Picture this, you're 475 meters beneath the Mediterranean Sea, deeper than the Empire State Building is tall. Above you, massive cargo ships cross one of the world's busiest shipping lanes. Around you, rock formations that have witnessed the collision of continents for millions of years. This is where Spain and Morocco want to dig the most challenging tunnel ever attempted. The Gibraltar Strait sits at one of Earth's most geologically violent intersections. For the past 6 million years, the African and Eurasian plates have been grinding against each other here, creating a landscape of underwater mountains, deep trenches, and fault lines that stretch for hundreds of kilometers. The water itself tells the story. Atlantic currents flowing east meet Mediterranean currents flowing west, creating an underwater battlefield of competing forces. Every day, over 300 ships navigate these waters. Oil tankers from the Middle East, container vessels from Asia, cruise ships packed with tourists. The strait ranks among the world's busiest shipping lanes, though it represents a smaller fraction of total global maritime traffic. Any tunnel must somehow coexist with this constant parade of massive vessels overhead. The Gibraltar Strait Tunnel isn't new. Engineers have dreamed about connecting Europe and Africa since the 1930s. Back then, Spanish researchers discovered something that killed the project immediately. The rock beneath the strait was so hard that their equipment couldn't even scratch it. The geological surveys revealed layers of limestone and dolomite compressed over millions of years into formations harder than concrete. Early planners considered alternatives. Some proposed a floating bridge with towers reaching nearly a kilometer into the sky. Others suggested an immersed tunnel, prefabricated sections lowered into a trench on the seafloor. Every option faced impossible challenges. The depths were too extreme. The seismic activity too unpredictable. The marine traffic too dense. They gave up. But nearly a century later, the dream is back, and this time they might actually have the technology to make it happen. Modern tunnel boring machines can cut through rock formations that would have destroyed 1930s equipment. Computer modeling can predict geological conditions with precision that early engineers couldn't imagine. Most importantly, successful underwater tunnels now exist as proof that the impossible can become routine. Here's what makes this project absolutely insane. The English Channel Tunnel, which everyone calls impossible when it was built, sits just 75 meters below sea level. The Gibraltar Tunnel will go 6 times deeper at 475 meters maximum depth. While the Channel Tunnel dealt with soft chalk that was relatively easy to dig through, Gibraltar forces engineers to bore through some of the hardest rock on Earth. The strait itself reaches depths of 900 meters, but the tunnel route carefully avoids these deepest sections. The numbers are staggering. 2 parallel tunnels, each around 28 kilometers for the underwater section, with total tunnel length reaching 38 to 42 kilometers, including land approaches. That's like building the Channel Tunnel underwater, but making it shorter while going much, much deeper. The maximum depth hits 475 meters below sea level, deeper than most skyscrapers at all. At those depths, the rock pressure is enormous. The temperatures climb higher than surface levels. Every meter forward becomes a battle against the planet itself. Engineers estimate they'll need to excavate millions cubic meters of rock and sediment. That's enough material to fill thousands of Olympic swimming pools. All of this debris must be transported to the surface through shafts that themselves represent major engineering challenges. The logistics alone boggle the mind. The tunnel boring machines required for this project will be among the largest ever built. Current technology maxes out at around 17.6 meters in diameter for the largest machines currently in operation. Gibraltar's planned tunnels will use machines measuring approximately 7.9 meters in diameter, large but within current technological capabilities. These mechanical beasts would still weigh thousands of tons and cost hundreds of millions of dollars each. But depth isn't even the worst problem. The Gibraltar Strait sits on one of Europe's most dangerous geological features, the Azores-Gibraltar Transform Fault. This isn't just any crack in the earth. This massive fault system stretches over 600 kilometers from the Azores Islands to the coast of Morocco. It represents the active boundary where three tectonic plates, African, Eurasian, and Iberian, meet and grind against each other. This fault line produced the devastating 1755 Lisbon earthquake, one of the most powerful quakes in recorded European history. Contemporary accounts describe church bells ringing across Europe from the vibrations. The tremor was so massive that people felt it as far away as Hamburg and even Finland. Lakes in Scotland reportedly sloshed back and forth for hours after the main shock. The resulting tsunami wiped out entire coastal communities across Portugal, Spain, and Morocco. Wave heights reached 15 meters in some areas, taller than a 4-story building. The port city of Lagos in Portugal was partially destroyed. Lisbon's royal palace disappeared beneath the waves. Modern estimates suggest that between 40,000 and 50,000 people died across the region, though some reports put the toll even higher. The fault remains active today. Seismic monitoring stations track regular movements as the African and Eurasian plates slowly grind against each other at about 4 millimeters per year. That might sound tiny, but over the decades it takes to build a tunnel, those forces add up. Engineers must design a structure that can flex and bend with earthquake activity without collapsing. Then there's the water problem. The strait connects two different seas, the Atlantic Ocean and Mediterranean Sea. Cold Atlantic waters constantly flow eastward, while warm Mediterranean waters flow westward, creating powerful underwater currents. These currents reach speeds that can knock diving equipment off course. Building tunnel sections in these conditions requires precision that has never been attempted at such depths. The water exchange between these seas is massive. Every second, roughly 1 million cubic meters of water flows through the strait. That's equivalent to emptying an entire Olympic swimming pool every 2 seconds, continuously, forever. This constant flow creates complex underwater weather patterns that change with tides, seasons, and atmospheric pressure. Marine life adds another layer of complexity. The strait serves as a critical migration corridor for whales, dolphins, and countless fish species. Sperm whales dive to depths of 1,000 meters here, hunting for giant squid in the deep trenches. Pilot whales travel in pods of hundreds. Any construction activity must account for these sensitive ecosystems. The underwater topography resembles an alien landscape. Steep underwater cliffs drop into abyssal plains. Rocky pinnacles rise like underwater mountains. The Cameronal Sill, an underwater ridge that separates the Atlantic from the Mediterranean, reaches depths of only 280 meters at its shallowest point. This ridge controls the water flow between the seas and represents one of the most challenging sections for tunnel construction. Spanish and Moroccan governments officially launched this project back in 1979 when their king signed an agreement to strengthen relationships between Europe and Africa. Two state companies formed, SECEGSA in Spain and SNED in Morocco. They spent millions on studies throughout the 1980s, but by 2009 the project died again. Too expensive, too risky, too complicated. What changed? The 2030 World Cup. Morocco, Spain, and Portugal will co-host the first World Cup ever held across 2 continents. Suddenly, connecting Europe and Africa by land became more than an engineering fantasy. It became a political necessity, tourism revenues, national pride, global attention. However, the tunnel will not be ready for the 2030 World Cup. Current projections put completion at 2040 or later. The numbers are compelling. FIFA estimates that the 2030 World Cup could attract over 5 million international visitors across the 3 host countries. Traditional travel between Spain and Morocco involves either flying or taking ferries across the strait. Flights require airport transfers, security delays, and weather-dependent schedules. Ferries take 35 minutes for the crossing, but require additional time for vehicle loading and port procedures. While the tunnel won't serve the 2030 World Cup, the tournament has created political momentum for the project. A high-speed rail tunnel would eventually revolutionize travel patterns between the continents. Journey times from Madrid to Casablanca could drop to under 4 hours, competitive with flying when you factor in airport delays. The economic impact extends far beyond tourism. Spain and Morocco have been strengthening trade relationships for decades. Morocco now ranks as Spain's fastest-growing trade partner in Africa. Spanish companies have invested heavily in Moroccan automotive manufacturing, renewable energy, and telecommunications. A direct rail link would accelerate these trends dramatically. Morocco's high-speed rail system changes everything. In 2018, Morocco launched Al Barak, Africa's first high-speed train. These sleek machines hit 320 kilometers per hour, connecting Tangier to Casablanca in just over 2 hours. The journey that once took nearly 5 hours by conventional rail now happens faster than most people's morning commute. Al Barak represents more than just fast trains. The entire system was designed with European integration in mind. The trains use French TGV technology adapted for Moroccan conditions. The electrical systems operate on the same standards as Spain's high-speed network. Even the track gauge matches European specifications perfectly. The investment was massive, over $2 billion for the initial 200-kilometer line, but the results speak for themselves. Al Barak has transported over 6 million passengers since opening, with ridership growing steadily each year. Business travelers now routinely commute between Morocco's major cities. Tourists can easily visit multiple destinations in a single trip. Current expansion plans are even more ambitious. Morocco is extending the high-speed line south to Marrakesh by 2029, adding another 430 kilometers of track. Eventually, the network could reach all the way to Agadir on the Atlantic coast, creating a 1,500-kilometer high-speed rail system spanning the entire country. Al Barak uses the same electrical systems and track gauge as Spain's high-speed network. That's not coincidence. Moroccan planners always intended their trains to eventually cross into Europe. The infrastructure already exists on both sides. The tunnel just needs to connect them. Current plans call for the tunnel to link Punta Paloma in southern Spain with Malabarta near Tangier in Morocco. That route avoids the deepest parts of the strait while still providing the shortest possible crossing. Trains would carry both passengers and vehicles, similar to the Channel Tunnel's shuttle service. But let's talk about what this really means. The tunnel would create the first permanent land connection between Europe and Africa since the continents separated millions of years ago. Trade routes that currently depend on slow maritime shipping could switch to rapid rail transport. A container leaving Morocco could reach Berlin faster than current sea routes reach London. The economic possibilities are massive. Morocco serves as a gateway to all of Africa. The country has become a major automotive manufacturing hub, producing car parts for European brands like Renault, Peugeot, and Ford. Moroccan factories now export over $10 billion worth of automotive products annually. With a direct rail link, these factories could integrate even more closely with European supply chains. Agriculture represents another huge opportunity. Morocco produces citrus fruits, vegetables, and other crops that European markets demand year-round. Currently, these products travel by truck to ports, then by ship to European destinations. A rail tunnel could cut transport times dramatically while reducing costs and environmental impact. The logistics industry is already preparing for this transformation. Major shipping companies are studying how a Gibraltar tunnel would affect their European-African routes. Some predict that rail transport could capture 30% or more of current maritime cargo volumes on certain routes. Tourism works both ways. European visitors could easily explore Morocco's imperial cities, Marrakesh, Fez, Casablanca, without the hassle of airports or ferry terminals. Weekend trips to Marrakesh from Madrid could become as common as Paris to London excursions. Meanwhile, North African tourists could access Europe's attractions with unprecedented convenience. The cultural implications are equally profound. A permanent land link would accelerate the exchange of ideas, languages, and traditions between continents. Students could easily study abroad. Workers could commute between countries. Families separated by the strait could maintain closer connections. Recent diplomatic developments make the tunnel more likely than ever. In late 2024, French President Emmanuel Macron visited Morocco for the first time in 6 years, signing agreements worth €10 billion. These deals specifically include expanding Morocco's high-speed rail network southward to Marrakesh, scheduled for completion before the 2030 World Cup. Funding remains one of the biggest challenges. Unlike the Channel Tunnel, which was privately financed, the Gibraltar project will likely require massive government investment from both Spain and Morocco. The European Union has already contributed for feasibility studies, suggesting potential support for the full project. International development banks are watching closely. The African Development Bank and European Investment Bank both funded Morocco's Al Barak high-speed line. These institutions could provide crucial financing for the tunnel project, especially given its potential to boost economic development across North Africa. Private investors are also expressing interest. Major construction companies like Bouygues, Vinci, and ACS have the expertise and financial resources to participate in such mega projects. The promise of decades-long operations and maintenance contracts makes the tunnel attractive despite the enormous upfront costs. The engineering challenges remain brutal. Swiss firm Lombardy Engineering, which helped design the Channel Tunnel, studied the Gibraltar project in 2006. Their conclusion? Technically possible, but far more complex than anything attempted before. The presence of two deep clay channels halfway across the strait complicates construction. These soft sediment layers could cause tunnel boring machines to get stuck or damaged. Modern tunnel boring technology has advanced significantly since 2006. The latest machines include sophisticated ground-penetrating radar that can detect geological changes ahead of the cutting face. Computer-controlled steering systems can adjust the tunnel path in real time to avoid obstacles. Improved cutting tools can handle mixed geological conditions that would have stopped earlier machines. The machines themselves are marvels of engineering. A typical tunnel boring machine for this project would measure around 7.9 meters in diameter and extend 200 meters in length, matching the technical specifications in current tunnel plans. These mechanical monsters weigh up to 4,000 tons and cost around 100 million euros each. They operate like underground factories, simultaneously excavating rock, installing concrete tunnel lining, and removing debris through conveyor systems. Seismic activity requires entirely new approaches to tunnel design. Traditional rigid concrete tunnels would crack during earthquakes. Engineers are exploring flexible joint systems that allow tunnel sections to move independently. Think of it like a giant underground snake that can bend without breaking. These joints must remain watertight while accommodating movements of several centimeters during major earthquakes. Japanese engineers have pioneered many of these techniques in response to their country's frequent seismic activity. The Seikan Tunnel, which connects Japan's main islands, operates successfully in one of the world's most earthquake-prone regions. However, the Seikan Tunnel reaches maximum depths of only 240 meters, half the depth planned for Gibraltar. Water pressure at maximum depth reaches levels that would crush conventional tunnel designs. The concrete walls need to be thick enough to withstand pressures equivalent to having several elephants standing on every square meter. Specialized waterproofing systems must prevent even tiny leaks that could gradually flood the tunnel. Temperature management becomes critical at such depths. Rock temperatures rise significantly below ground. Add the heat generated by high-speed trains, electrical systems, and ventilation equipment, and the tunnel could become dangerously hot. Cooling systems must operate continuously to maintain safe conditions. Emergency procedures require completely new thinking. If something goes wrong in the Channel Tunnel, rescue teams can reach any point within 30 minutes. In the Gibraltar Tunnel, the deeper sections could take much longer to access. Escape routes, emergency chambers, and backup systems must account for the extreme environment. Current construction timelines no longer target 2030. Recent reports suggest completion has slipped to 2040 or later, which is probably realistic given the enormous technical challenges. The Channel Tunnel took 6 years to build through relatively simple geology. Gibraltar's harsh conditions could easily extend that timeline significantly. The geopolitical implications extend far beyond transportation. A permanent link between Europe and Africa would fundamentally alter trade relationships and cultural exchange. European leaders see Morocco as a stable partner in an increasingly unstable region. The tunnel represents a massive bet on continued cooperation. But criticism exists too. Environmental groups worry about disturbing sensitive marine ecosystems. The strait supports diverse wildlife, including migration routes for whales and dolphins. Construction activities could disrupt these patterns permanently. Some economists question whether the tunnel makes financial sense. High-speed rail works best for distances between 200 and 800 kilometers. Beyond that range, aircraft become more competitive. Madrid to Casablanca covers about 900 kilometers, right at the edge of rail's effectiveness. Security concerns also loom large. A permanent land connection between continents could facilitate illegal immigration or smuggling. Border controls would need to be absolutely airtight. Any security failure could undermine political support for the entire entire project. Technical alternatives exist. Some engineers propose floating tunnels, underwater tubes anchored to the seabed but not buried beneath it. These structures could avoid the deepest rock formations while still providing a fixed crossing. However, floating tunnels have never been built at Gibraltar's scale or depth. Bridge options remain technically impossible. The strait's 900-meter depth would require support towers taller than any structure ever built. The seismic activity and marine traffic make bridges completely impractical. If this crossing gets built, it will definitely be a tunnel. Regional competitors are watching closely. Turkey is building massive infrastructure projects connecting Europe and Asia. Russia has discussed tunnels across various straits. China's Belt and Road Initiative includes multiple underwater crossings. The Gibraltar Tunnel represents Europe's answer to these ambitious connectivity projects. Looking ahead, success depends on sustained political will from both governments. Megaprojects typically span multiple election cycles. New leaders must remain committed to their predecessors' visions. Economic crises, political instability, or diplomatic tensions could easily derail the project. Technical advances in tunneling technology improve the odds. Tunnel boring machines have become larger, more powerful, and more precise since the Channel Tunnel era. Computer modeling can predict geological conditions with unprecedented accuracy. These improvements might make Gibraltar's challenges manageable. The 2030 World Cup provides a firm deadline that concentrates minds and budgets. Major sporting events have historically driven infrastructure development. Japan built its bullet train network for the 1964 Olympics. China constructed massive transportation systems for the 2008 Olympics. Morocco, Spain, and Portugal have similar motivation for 2030. Whether the tunnel actually gets built depends on factors beyond pure engineering. Political stability, economic growth, technological advances, and international cooperation must all align perfectly. The margin for error remains extremely thin. Current feasibility studies project the tunnel could carry approximately 12.8 million passengers annually, though these remain estimates subject to change as the project develops. That's roughly the population of Belgium crossing between continents every year. Freight capacity projections suggest the tunnel could handle significant portions of Europe-Africa trade, though exact volumes depend on pricing and logistics arrangements. The economic impacts would ripple across both continents. But we've heard ambitious promises before. The 1930s studies promised a Gibraltar crossing within decades. The 1980s revival generated similar optimism. Previous generations of engineers couldn't deliver. This generation faces the same fundamental challenges, plus new complexities. The Gibraltar Tunnel represents a boldest attempt to reshape geography through engineering. Success would create the first permanent link between Europe and Africa since the continents separated. Failure would remind us that some barriers exist for good reasons. With just 5 years until the 2030 World Cup, we're about to discover whether modern technology can finally conquer one of Earth's most stubborn obstacles. Let us know what you think about this in the comments section. The question isn't whether we can dig through 900 meters of rock beneath one of the world's most active seismic zones. The question is whether we should, because once you connect two continents, there's no going back.